Contained in this bundle is a fossil which supports the controversial idea that birds are the direct descendants of dinosaurs. Discovered just 2 months ago, it and other fossil finds from China are sending shockwaves throughout the world of paleontology.
I'm so excited by the developments in China that I can't talk about it enough. I think we've been shown there's a whole new chapter of geologic time preserved in China.
John Ostrom's excitement over these Chinese fossils is because they seem to confirm a radical theory he first proposed 30 years ago. He has long been fascinated by the origin of birds.
I can't think of anything more interesting than trying to understand how powered flight in birds might have come about. I think birds, as we know them, had a dinosaur ancestor.
Not everyone agrees. His most ardent critic has been ornithologist Alan Fiducia.
It seems almost inconceivable that birds could have evolved from dinosaurs. Dinosaurs simply have too much baggage. They're already ground-dwelling creatures with large balancing tails. This is the absolute worst kind of body plan to imagine flight evolving from.
Designed specifically to jump at and kill its prey with downstroke of the claws of the feet. It was slicing its prey to death.
Deinonychus reinvented our view of dinosaurs. No longer were they seen as slow and stupid. They could be agile and smart, perhaps even warm-blooded.
I was pleased that there was so much positive reaction. But very soon I realized that there are more skeptics out there than there are believers.
Well, the dinosaur bird theory has tremendous popular appeal. One can vicariously study dinosaurs at the backyard bird feeder. And one can go get a piece.
Call this type of coincidence convergent evolution.
One of the most dramatic examples of convergence are the ancient fish reptiles and living porpoises or dolphins. They're superficially almost identical, but when one looks at the structure in detail, the similarities fall down.
Dolphins are air-breathing mammals, while the ichthyosaur was an ancient marine reptile. They belong to entirely different animal groups, yet look so similar because they've both evolved to be highly streamlined.
Convergence is a pervasive phenomenon. And that's what we're seeing with birds and dinosaurs. When birds become ground-dwelling creatures, they come to look very much like these predatory dinosaurs. And most methodologies have a hard time sorting out convergence versus relationships.
Central to John Ostrom's argument was the existence of a feathered dinosaur. Without this missing link, his theory remained speculative and marginalized. But as the years passed, a few paleontologists began to take his ideas more seriously. Two of his strongest advocates are based at the American Museum of Natural History in New York. Louise Chiappi on the right studies fossil birds, while Mark Norell is an expert on predatory dinosaurs. These subjects now overlap.
Well, John Ostrom was really one of the first ones in the modern era in the mid-60s to talk about dinosaurs being related to birds.
His connection between dinosaurs and birds was also, for me, very important because I needed to know the sources of the birds I was studying.
He made a series of very, very careful comparisons of these kind of animals with Archaeopteryx and really realize the similarity between the two.
Now that we've found all this new stuff,
Yeah,
we really
okay.
know that these things should be a lot closer
Much
together.
closer.
When you mention dinosaurs, people think of things like the giant sauropod dinosaurs or Tyrannosaurus and things. The thing is back in the last century, people went out and they collected the biggest bones they could find. But in fact, there's a whole range of size of dinosaurs, all the way from big ones like that to little ones. It's much like mammals. I mean, we have things like elephants today. We have things like shrews today. Unfortunately, the fossils of shrews are much harder to find than the fossils of elephants. The same as with dinosaurs. But now we're starting to find lots of these small animals, and it just so happens a lot of these small animals, like Velociraptor, are the ones which are most closely related to birds.
Contrary to popular belief, Velociraptor was only the size of a turkey. The producers of Jurassic Park decided to make it much bigger.
I hardly think that an animal that looks like this, which is kind of an ankle biter, would be able to terrorize the people that it did in Jurassic Park.
Small predatory dinosaurs were the key link to birds. The recent Chinese fossils are even smaller than Velociraptor.
Well, I think that really that these fossils, I think, are as significant for the particular questions which, Luis and I are interested in, as far as the origin of birds. They're as exciting as Archaeopteryx, and even in some ways more so, because the Archaeopteryx is really a full-fledged bird already. What we're looking at is we're looking at things which really document the transition from typical dinosaurs to birds, and this is some great stuff.
Right.
In a remote corner of northeastern China, there were rumors of amazing animals preserved in rock. At first, local people thought they were the remains of dragons, but they turned out to be some of the best preserved fossils in the world. Ji Chang, director of the Beijing Museum of Geology, is now in charge of the dig site.
这个大白喇子有一盘它比较硬，它叫大白喇。
要化石的保存的非常好的，必须具备两个条件，一个就是迅速埋藏，使它处在一个环氧环境之中；第二个条件就是不让它有水流的搬运。那么从四合城这个地质情况来看的话，它具备了这两个条件了。所以你们看这个，它这一套沉积岩基本上是火山灰雾这所沉积下来的，非常的细，非常的细，这也给这个化石的保存很好的保存创造了条件。
Picture the scene during the age of dinosaurs. An area of tranquil lakes is convulsed by erupting volcanoes. Clouds of poisonous gas kill birds and other animals, their bodies slowly sinking to the bottom of the lakes. Over time, layers of sediment and volcanic dust entomb them. Here, the animals are to remain for over 100 million years. The fossils are exquisite. The individual ribs of a fish, the delicate wings of a dragonfly. Even more impressive were the feathers belonging to ancient birds, birds only slightly more advanced than Archaeopteryx. It was these creatures that had been mistaken for dragons. Fossil birds are extremely rare, and so it was at this time that Ji Chang first heard about the fossils and got involved. All the work up to then had not been done by paleontologists. Rather, the fossils had been found by farmers. 3 years ago, farmers from local villages started to collect fossils to sell. They have been hard at it. The entire site has been excavated by hand, turning up many of the ancient bird fossils. But then in 1996, local farmer Li Fang made an even more important discovery.
当时挖到一块大石板，在石头中间砸开以后，在这个钻茬发现这骨茬，当时很高兴，认为是一个很珍贵的东西。但是当时就凭断裂的地方，看不出来是什么东西。当时连整个的一块石板都抬了下去。
It turned out to have the anatomy of a dinosaur, with what appeared to be a fringe of feathers running along its back. Could it really be a feathered dinosaur?
我一直认为石河城的老乡发现这个化石，尤其在鸟类起源研究上，它的作用是非常大，做出了非常大的贡献。可以这么说，没有他们的发现，就没有我们现在的研究成果。
通过实验必须有可能是比他们经验丰富一点。
为什么？
通过自己亲身实验的，自己挖掘的搞出来的经验。
Since Li Fang's discovery, other feathered dinosaurs have been found. The latest one has been named feathered tail, or Caudipteryx.
Caudipteryx 如果要是把那边能修复的话，那更好了。这个羽毛细语非常清楚。
尾巴有多少节能看出来吗？
These fossils could be the missing link between dinosaurs and birds that John Ostrom was so desperately hoping for. If so, they would be some of the most important fossils in the world.
鸟类起源问题不是一个中国人仅仅是中国的事儿，而是一个国际科学家都想解决的一个问题。所以这也就是我为什么一直提倡研究这个鸟类起源问题的，那么要进行组成一个国际的科学研究队伍，那么进行科技合作。
Especially, bone-wise, they're clearly not birds.
If it's true, it's really going to change the way that everybody thinks about these problems.
Well, we hope that.
Yeah, and it's always nice to be back in Beijing.
That's right.
不该爱的人，你的心中满是伤痕。你说你犯了不该犯的错，心中满是悔恨。你说你尝尽了生活的找不到。
I think that right now we're at a really unique opportunity. Ji Chang and the people from the Geological Museum of China are really wonderful in wanting to have an international collaboration on these things. That we're going to get to see specimens to try to do a more in-depth analysis on these and try to bring these into the larger context of some of the issues which we're working on.
So this is it, huh? Yeah. This is the new specimen. Yeah, you see. So here you see all the long-tailed feathers, right? Yeah. Well, we've got body feathers and tail feathers, and looking at them the way they branch, you can't argue about them being true feathers or not. The arms are amazingly short, I mean, especially compared to the hind leg. I mean, even though it has feathers, there's no way this animal could fly. Nice specimen. Oh, thank you.
These new fossil animals were remarkable. They were dinosaurs, but they had feathers. They didn't look as if they could fly, but they had feathers. So what were the feathers for? Biologist Jeremy Rayner knows more about feathers than most people. A lot depends on their detailed structure. Tiny hooks hold the strands of the feather together to create a smooth aerodynamic surface.
Birds wouldn't be birds without feathers. Feathers are one of the most extraordinary structures in nature. Incredible complexity, yet the whole thing's built from one cell. There's no blood supply going into the feather. This is a feather of a swan. You can always tell a flight feather because they're asymmetric. In this case it's extreme, but the shaft runs off-center. The wing works as an aerofoil, each feather works as an aerofoil, and the force on the aerofoil is concentrated near the leading edge. So as the air approaches this side of the feather, the stiffest part is where the force is biggest. It means the feather changes shape in just the right way the bird needs when it flies.
This has made it possible to verify that Archaeopteryx could fly.
The feathers on the wings of Archaeopteryx are certainly asymmetric. You could look at one of these feathers and you'd be hard put to tell that it wasn't the feather of a perfectly ordinary modern bird. It's an asymmetric feather, generates force in flight, presumably just the same way that a modern pigeon or gull or any other species would.
But Caudipteryx, the new Chinese fossil, had symmetrical feathers. This not only confirmed that it couldn't fly, but it also suggests that feathers first evolved for a reason other than flight.
Actually, there's three main functions that feathers could have. One is flight, which with these specimens I think we can begin to sort of rule out. The second is feathers are, as we all know when we wear down parkas or anything else, are wonderful insulators. So the origin of feathers, especially of the plumulaceous or body feathers, the downy feathers, could easily be interpreted as a characteristic that's related to the origin of an advanced metabolism where the animals were basically warm-blooded. And the third one is they could have originated for a display purposes, for either some sort of sexual selection or territorial displays or something else. And looking at the distribution of feathers on these early protobirds, it sort of suggests that. I mean, they have these big plumes of feathers at the end of their tails, sort of like kind of primitive peacocks or something.
Alan Fiducia is skeptical of the new Chinese finds. He believes that feathers evolved for flight first of all, and only much later were they adapted for display or for warmth.
It seems very doubtful that feathers evolved initially for the purpose of insulation. Everything we see about feathers relates to aerodynamic function. They're very expensive, both from the standpoint of development and structure, maintenance. And to imagine clothing a dinosaur with feathers would be tantamount to insulating an ice truck with heat shields from the space shuttle. It's gross evolutionary overkill, and it really makes no sense.
However, G, Norell, and Chiappi do think it makes sense. For them, Caudipteryx and the other Chinese fossils were feathered dinosaurs. Moreover, feathers evolved before the evolution of flight itself. Caudipteryx possessed feathers on its short arms and its tail. Crucially, the feathers were symmetrical and so useless for flight. The feathers on the body perhaps kept it warm. The feathers on the tail were probably for display. And if it was like many other dinosaurs, Caudipteryx almost certainly nested its eggs. But a mystery remained. If Caudipteryx really was a missing link between dinosaurs and birds, how did its descendants ever get off the ground? How do you evolve from a ground-dwelling feathered dinosaur to a flapping, flying bird? What do you need for powered flight?
The aircraft's designed to do exactly the same thing as a bird. The obvious feature it has, first of all, is these enormous wings. The wings have got exactly the same sort of aerofoil cross-section as a bird wing does. It's very smooth, it tapers down to a point at the back, and it's slightly tilted. And that tilt, that asymmetry, is what gives the wing its lift. But where the analogy with a bird breaks down is that these wings will only produce an upwards force. The bird has got to produce a forwards force, and it does it by flapping. The aircraft gets its forward force completely differently. It has the engine on the front. Nature hasn't come up with an engine. So the bird wing is not only producing the thrust, analogous to this, but it's supporting the weight using the wing like this. Exactly the same mechanism, but it has to flap. You can see in this bird, the buzzard, during the downstroke, the wings are fully stretched, extended maximum wingspan to produce a maximum force. As you go into the upstroke, the wings moving up relative to the body, the wings flex slightly. The wings have to be slightly shorter, so that the force from the upstroke isn't quite so big. It does that simply by flexing the wrist, moves the feathers of the hand of the wing backwards inside the wing. It's plane. And during the upstroke, the wing's a little shorter. Then as it comes to the end of the upstroke, the wing flexes forwards and goes into the next downstroke, and again the wing is fully stretched.
To understand how the wing could be so flexible, it's necessary to view inside the bird. At the University of Montana Flight Laboratory, scientists have taken unique X-ray footage of a magpie in flight. The special-shaped wrist bone and the elbow joint work together to pull the wing in on the upstroke and then push it out on the downstroke, 12 times every second. According to John Ostrom, the bird's flexible arms were inherited from their dinosaur ancestors. Deinonychus had the same type of wrist to grasp its prey. Chordipteryx also had this distinctive wrist. And Archaeopteryx was to use this wrist to flap its wings. Even so, research has suggested Archaeopteryx was a poor flyer. It was still only a primitive bird.
I've got here a simple outline of Archaeopteryx. It looks a very chunky bird because compared to other species its wings are very short. It's got a very big tail, much bigger than most other bird species. But the shape of the wing isn't too different from quite a lot of birds you could see around nowadays. Birds like magpies, the cuckoos and some tropical cuckoos are very similar. It's hard to be very certain about what Archaeopteryx could do and how it flew. I think it was very effective in normal forward flight, the sort of cruising flight a bird might use for moderate distance. The difficult thing for a bird isn't that, it's taking off and landing, hovering, changing flight direction, escaping predators. All these things, sudden and rapid and very controlled movements. And this I don't think Archaeopteryx could do. I think it was probably quite a clumsy flyer.
Clumsy flyer or not, the first bird must have got airborne somehow. John Ostrom argued that primitive birds evolved from ground-living dinosaurs running so quickly that they literally took off. This is known as the ground-up theory.
One problem with the ground-up theory for the origin of flight is that it's very difficult to explain how it might have occurred. And in fact, in every group of living vertebrates, there are examples of parachuting or gliding organisms. They fly to some extent. This includes frogs, lizards, snakes that hurled themselves out of trees with special adaptations, and a variety of mammals, probably 15 or 20 types of mammals, including sugar gliders, flying lemurs, flying squirrels, flying rodents, and so forth. And in every case where a group of vertebrates has taken to the air, they have one thing in common. They evolve flight from the trees down.
John Ostrom disagreed. He reasoned that flapping flight was more important than gliding flight.
Flapping flight or powered flight as we see it in modern birds and apparently existed in Archaeopteryx did not come through a gliding phase. Gliders depend upon a stable, immobile airfoil to support the lifting surface. Flapping flight depends on flexibility in that airfoil surface, and that's what birds possess. I think the ground-up idea makes sense.
Taking off from ground level was always going to be harder than leaping from a height. This had been a problem for the ground-up theory, but recent research has made it more plausible. Scientists at the University of Texas used the master of flight, the hummingbird, to carry out a range of ingenious experiments.
This is Frank.
Frank, okay. And how old is Frank?
Oh, Frank is young.
They altered the density of the air in a sealed chamber by pumping in the extremely light gas, helium. They have found that air density affects the ability of birds to fly.
What's the flow rate over there?
5 liters per minute.
All right, 5 liters per minute. Let's let the air density decline. If we reduce air density, we make the air thinner, and we make it harder for the hummingbirds to fly, and eventually induce aerodynamic failure. We literally get the birds to drop out of the air. If we then increase air density, the birds can come right back up to their perch.
It's a crucial discovery because the atmosphere during the age of the dinosaurs was different from today's. Levels of oxygen and dense gas were much higher then, making it easier for primitive birds to fly. Extra oxygen would have helped for another reason. Flying is hard work, and birds have to breathe quickly to get enough oxygen to the flight muscles. Here, a heat-sensitive camera shows the muscles glowing red. More oxygen makes it easier to power the muscles. The oxygen of the Jurassic atmosphere would have been critical for birds on the cusp of true flight.
I think that the effect would have been much more pronounced then, because flight literally is a question of getting off the ground, and anything that even incrementally increases the likelihood of getting airborne is going to select positively for evolution of flight. Particularly for birds, I think this would have been a profound change.
The first flight was a momentous event. Landlocked dinosaurs had evolved into airborne Archaeopteryx to eventually develop into something as advanced as hummingbirds. But Alan Fiducia doesn't believe the evolution of birds started like this. His most recent criticism came from the laboratory. It's nothing to do with oxygen or feathers. It's all to do with fingers. This is the hand of a human embryo. We have 5 fingers because we descend from primordial amphibians, which also had 5 fingers. Throughout evolution, humans have retained the same number of digits. But certain animals have lost some of their fingers. Birds only have 3 fingers remaining on each hand, as did the predatory dinosaurs.
And of course the question is, which 3 fingers? So this is an obvious way of testing whether birds are related to dinosaurs. Are the same 3 fingers involved? We know that dinosaurs have the first 3 fingers. Fingers 1, the thumb, and the next 2 fingers. We know this because Triassic dinosaurs show fingers 4 and 5 being reduced.
In order to find out which 3 fingers birds have, they studied the hand structure of a variety of bird embryos.
And what we found was an amazingly conservative pattern, allowing us to identify the digits beyond any question. And interestingly, the 3 fingers in the bird hand are not digits 1, 2, 3, but in fact are the 3 middle fingers, digits 2, 3, and 4. So in order to switch from the dinosaur hand to a hand with fingers 2, 3, 4, one would have to reorganize the entire development of the hand. It seems extraordinarily improbable.
We have to remember that there's over 100 characters which link dinosaurs with birds. So if you find one characteristic, like the embryological evidence of a hand, that seems to disagree with that, then you have to create a special explanation for why the other 100 characters are all the same. So, granted, at this point, it looks like some incongruous evidence. But nevertheless, as I'm confident with more study, it's just going to be a single character which will be interpreted within the greater scheme of all the evidence put together.
The debate has really been dichotomized between ornithologists and paleontologists. And a lot of it relates to their backgrounds. Ornithologists view Archaeopteryx as tree-dwelling, fairly typical birds, albeit primitive. Paleontologists view these forms as feathered dinosaurs. So in fact, the background, I think, of the various scientists involved has played a rather dramatic role in how we interpret the fossil record.
Well, it's a heated debate, yes, but I mean that we work hard on this stuff. We care about this stuff. I mean, if we weren't passionate about this stuff, we should be doing something else because, I mean, it does require a lot of work.
We're a tall lad, flap the druid in the old days.
Hornet 3, which is a modern bird.
Ride a white swan that the people of a Belgium, where you headlong, baby, can't go wrong.
Here you have Caudipteryx and Protarchaeopteryx, the new Chinese fossils, which fall.
Never mind birds evolved from dinosaurs. Mark Norell goes even further.
Birds and dinosaurs are incredibly closely related, so much so that I would contend that birds are a kind of dinosaur. Just like humans are a kind of primate and a kind of mammal, birds are dinosaurs and they're reptiles.
Dinosaurs did not die out. I mean, not all of them became extinct. Only a portion of them became extinct, and another portion of them, the birds, didn't, and they're, as we know, around us.
Today, according to Norell and Chiappi, there are nearly 10,000 species of dinosaurs, occupying every niche imaginable.
Who is the position here? Are you satisfied with that?
Modern birds have come a long, long way from Caudipteryx. Better flying skills, ever lighter bones. And over 100 million years ago, the primitive bird, Confucius ornis, evolved the first known beak.
Confucius is very interesting since it documents the transition from very primitive flyers, such as Archaeopteryx, and sophisticated flyers as modern birds. The beak is widespread among modern birds. There is no bird today with teeth. But in the age of dinosaurs, most of the birds had teeth. Confucius ornis and some others evolved independently a beak, and they lost their teeth, presumably as an adaptation for feeding.
Teeth became beaks. Scales became feathers. But somewhere within the genes of modern birds remain the vestiges of reptiles. Remarkable work on the frontier of science has provided more evidence of this link to reptiles. There's a saying, as rare as hen's teeth. At this laboratory in Connecticut, scientists have tried to prove the saying wrong by creating teeth from the beak of a chick embryo. They have discovered that the tissue of a chick that will eventually form the beak retains the potential to create the essential ingredient of all teeth, dentine.
Well, we're very interested in understanding the process of tooth development. While the results may eventually be useful for things like tooth regeneration in people who may have lost their tooth due to disease or accidents, or people who have no teeth at all, we may be able to induce tooth formation, that is in people who have no tooth because of genetic defects.
The scientists used a particular protein to trigger the chick tissue into making dentine. In a few experiments, whole teeth were created. Over several weeks, they slowly emerged. A single tooth from a reptilian past.
A very well-formed tooth with nicely formed roots here, and surrounding it we have a bit of bone over here.
So here we can see, this is the enamel, and it's derived from the chicken tissue, and the mesenchyme is determine the shape of the tooth.
One of the things that these experiments do demonstrate is that within the chick genome that there still exists the genes for the structural components of teeth, even though they may not have been used for many millions of years. Birds contain the genes to make teeth, but in order for them to be turned on, they require a signal or protein from another tissue to cause them to turn on and then form the teeth.
Could this be another approach to Jurassic Park? In the film, scientists recreated dinosaurs from DNA taken from the blood of mosquitoes trapped in amber. This is now thought to be impossible because of contamination. But recently, a paleontologist has proposed that tampering with the genes of modern birds might be the best way to bring dinosaurs back. It's wild speculation, but it might just work. Take out the beak genes, and the fullback is a jaw full of teeth. Remove the feather genes, and the fullback is scales. Take out the wing genes, and the fullback is arms. And voila, a small predatory dinosaur.
The prospect of trying to recreate a dinosaur from present-day birds, although theoretically possible, it's really hard for me to comprehend that anything like that could really occur within my lifetime.
I don't think we have to recreate a dinosaur from a bird because birds are dinosaurs. But beyond that, people who propose these kind of things, I mean, I'm really not interested in that stuff. I mean, that's sort of outside the realm of science.
For generations, scientists have been puzzling over the origin of birds. Did they arise from dinosaurs? And if so, which ones?
Back in the realm of science, a conference in July 1998 celebrated the discovery of the Chinese fossils.
We are honored that Dr. Ostrom is with us in the audience today as an observer. Would you mind standing, Dr. Ostrom?
Mark Norell and Ji Chiang talked about their scientific paper based on the finds. For those present, John Ostrom's theory has been fully vindicated.
Well, it's very satisfying for me to see how much interest there is even thinking about how birds learn to fly and began to fly. I think it's the most exciting moment of my career. And I'm satisfied that apparently I stirred up a lot of thought.
我相信 John 是非常和我一样的是非常兴奋的， 在他当代70年代的时候，他是非常孤立的，他非常是一个少数派。那么现在中国的材料突然发现了，我相信他跟我一样，他发现了最重要的证据，支持了他的过去的那种假设。那么是这种假设变成现实的话，我认为他也会支持我，我也会回他同样的感觉。
However, the latest fossils are a problem for Alan Fiducia. Now he is very much in the minority.
I've been involved in this debate for several decades, and I think ultimately the evidence against the dinosaurian origin of birds is going to be overwhelming.
I remember how anxious I was to persuade my colleagues to go back and look at the evidence and look at it in new light. So I am very sympathetic to the position that Alan seems to be getting in now because of the new finds.
The debate's over within the scientific community. I mean, it's done. There's just a couple of people who are still holding on, who happen to be particularly vocal in their commentary about it. But in the professional community, it's definitely a minority, and a very small minority at that.
Well, we're outnumbered in terms of advocates of the dinosaurian origin of birds, but fortunately, science doesn't operate by vote.
It's unlikely that the Royal Society for the Protection of Birds will be changing its title in the near future, but this revolution in paleontology may mean that you never observe the birds around you in the same way again.
Mm-hmm.